Good afternoon, everybody. I'd like to thank you, first of all, for spending the time to come out here and join us for today's webinar on root cause analysis when CFD results and experimental data don't match. My name is Michael Nee. I'm a product manager here at Aerodynamic Solutions. Let me first introduce you to today's speakers. Dr. Ron-Ho Nee, he is the founder and CTO of Aerodynamic Solutions. Prior to founding Aerodynamic Solutions in 2008, Bob worked at Pratt & Whitney, where he was a senior fellow in both aerodynamics and CFD methods. Next is Mr. William Humber. He's our senior CFD engineer at Aerodynamic Solutions. Prior to joining Aerodynamic Solutions, Will worked in the turbine durability group at Pratt & Whitney, and he received his BS and MS at Penn State University. Again, my name is Michael Nee. I'm a product manager here, and with that, I'm going to hand it over to Bob to take us through this presentation. Bob?
Thank you. Thank you for welcome you to attend this webinar. And the title of this webinar is Root Cause Analysis. The root cause analysis about when the experimental data and the CFD do not match. How to find the root cause. First of all, we'd like to know what's the overall objective. We need to understand CFD is only a tool for flow predictions, and they vary. The results vary from solver to solver, mesh to mesh, and user to users. That will have to realize this fact. Second, if you want to use a CFD as a tool to design, CFD method must be validated before it can be used. I want to emphasize the validation instead of calibration. We like to validate the methods. And to validate methods, a strong root cause analysis method is really required to achieve that goal. So, before do any root cause analysis, the first question we'd ask, there's many questions we'd ask ourselves, right? First is, what is the overall objective of comparing CFD results against data? We plan to, of course, most people want to make sure the CFD do the job right and can be used as part of a design of your product or improve your current product. Now, when the data is not matching with the experiment, the question always, glass half full or half empty? Now we need to answer the question, how close they should be. They must be. Because, you can be defined 1% your target, 5% your target. Depends on applications. But also need to understand how the data on the CFD being analyzed. Once we understand how close they should be, then if they are really different beyond your expectation, we will ask our question, where does the difference really come from? We have been working on this problem quite a few number of years, even before we form our own company. I believe a lot of people attending this conference or webinar truly have the similar experience as we have. So we struggled through for many years, and sometimes those information was not shared among many engineers, both from CFD area as well as from experimentalists. We always work hard, try to find the root cause, the difference of root cause, but generally those hard work is not reported in open literature. Now, we believe this is very important process so that we would like to share with you. So our process categorized the possible root cause in 5 categories. And on this chart, we show 5 items, but those are not in specific order. The first item we show is always because we ourselves, our company, ADS CFD, our aerodynamic solution is focused on CFD tool development. So we always look inward. If the CFD code have problem, what do I mean by problem? You know, there's a limitation of the code we are using. What kind of limitation? Do we have good enough turbulence model to address the issue? When we do the analysis, we assume the flow steady state instead of a truly unsteady flow problem. Or we choose the right approximation. Those are what we call CFD modeling problem. That's first and foremost from the guy who working on CFD. Looking inwards, must be something wrong we have done when the data is not matching. However, on the other hand, there are additional items we must look into. Second item, I think, is of critical importance. We have encountered many of these situations. In other words, what I try to say is simulated geometry is not consistent with the experimental geometry the experiment was carried out. So the two geometry is not the same. If we not looking into this geometry issue, no matter what we do in turbulence model and improve our simulation, if the match data, you're lucky, not lucky, I think you're unlucky now. You no longer have a tool where you can use for prediction. Because if you run geometry, there's no chance for you to match that data. But if you match the data, you're walking down to a very dangerous path. So I want to make sure simulate geometry, make sure is equal to geometry that have been tested or to be tested. Third item is critical feature not modeled. And I will give you an example, very difficult to explain what we mean by critical features. Okay. Today's presentation will highlight one of them. The fourth and most important item solving the problem is your boundary condition and initial conditions. So we have to pay attention to those areas. The last category is that we need to understand how the experiment data being reduced and how they'll be presented consistently between CFD results and experimental data. So those 5 areas, one need to pay attention to go through to figure out what's the cause that CFD results not matching with experimental data. So today's presentation is focused on our experience, our CFD tools. So this chart to tell you a little bit about our tool, our company. As Michael a while ago mentioned, our company formed in 2008. But before 2008, I retired from Pratt & Whitney in 2003. After 1 year, people asked me to consult and do CFD analysis. So I say, okay, instead of using some commercial software, maybe I should rewrite the software I developed when I work at Pratt & Whitney as a senior fellow and the engineer over there. So in 2004, we start rewrite the CFD system, which consists of most important 2 parts. First, the flow solver, we call CodeLeo. That code can handle both structure mesh and unstructured mesh, and handle general flow configuration. What I mean is very low speed all the way to Mach 3, can do steady, can do unsteady, so on and so forth. The second code we wrote is very specific mesh generator for turbo machinery application called code WANG, as shown here. So those are code we are using to do, to carry out. We encounter many issues about experiment data not matching with our numerical results. So we are really talking about the tool in here and our experience. So we today bring you 3 major examples showing that the process and causes we have been identified for each of those test cases. First, example 1. It is a centrifugal compressor flow simulations. We compare our analysis against available test data. So what case I'm talking about is shown on next chart. It's a NASA centrifugal compressor build 3. It is a 4-to-1 pressure ratio centrifugal compressor with a splitter. 15 main blades with 15 splitters. And the cross section and the impeller are shown on top of the figure. The experimental setup on your left-hand side. On the right-hand side is the mesh associated with the impeller with the splitter. This CC3 results being published in many in the report and in the technical presentations. And I highlight here is one NASA technical report 107541, and also highlight the presentation at the ASME conference in 1997. Okay, in the technical paper, they provide performance results of this compressor. I just directly scan the output and present in this chart. You see a total of 4 charts in front of you. On the left-hand side is a performance map for the centrifugal compressor stage, which has vented diffusers. On the left-hand side is performance map for the 4-to-1 pressure ratio compressor without vents, called ventless diffusers. And up and lower chart, upper present the efficiency, adiabatic efficiency of the compressor, and the lower represent pressure ratio. There are 5 speed lines associated with each chart, starting 60%, 70%, 60%, 70%, 80, 90, and 100% speeds. For both vented diffuser centrifugal stage and ventless stage. We received airfoil geometry from NASA in year 2005. And the geometry definition is pretty interesting. For the centrifugal compressor impeller, they have open trailing edge. And we analyze using our code WANG generator mesh. Our initial results can be shown on next chart. This is a compressor performance map at 100% speed. The blue dot is experimental data for the ventless diffuser. The magenta color is our very first initial simulation use code WANG and code LEO. We find the experimental results and our CFD analysis really way off in terms of pressure ratio. the pressure ratio measured at the flow about 8 pounds per second is 4.5 or 4.4 something. Our calculation 4.9. That's almost 10% difference in pressure ratio. Efficiency is a little bit better. The range is smaller. So I believe many people will encounter a similar problem at the very beginning of the first simulation. Why the calculation are so different from the experiment data. So we went through many root causes and maybe ask ourselves, is turbulence level is right? Is surface roughness is right? Is the geometry we missed? Is the boundary condition we not put in right? Once through all of that, the next chart showing one of the most interesting and amazing output from my perspective. What you're seeing here is the 50% span pressure, I think Mach number distribution at 50% span around trailing edge of the impeller and the splitter. On your left-hand side is the mesh we originally generated, because we've been working, I myself been working on the axial compressor and axial turbine. Generally, those geometries have rounded trailing edge. However, in the experiment of centrifugal compressor, people generally cut off the trailing edge at constant radius, which no longer rounded trailing edge. They are very sharp and are really at a constant radius. However, this impeller is pretty long. You know, the difference of the geometry as originally thought is not as important. But I say, wow, maybe we should look at it, whether this trailing edge make a major difference. So we went through the analysis, carry out the simulation. Long and behold, we find the following results. This is the results from rounded trailing edge versus the trailing edge constant radius cut. Again, let me repeat myself. This is the pressure ratio versus flow. The blue dots is experimental data. Our initial results is a magenta color. By changing the trailing edge shape from rounded trailing edge to a constant radius cut trailing edge, we find the pressure ratio coming down much closer to the data than initial simulation. Used to be 10% error, now about 4% error. What about efficiency? Efficiency shown on the other side. Overall efficiency trend didn't change much. But so what's the learning? What we learn is correct airfoil geometry is critical to the performance of this specific centrifugal compressors. Will impact the pressure ratio highly for this design. What's special about this design? This design have a back swept of the trailing edge about 45 to 50 degrees. Okay, so we identify one of the causes why the analysis is so different from experimental data, because we did not really include the right geometry in our simulation. So also I mentioned we have searched for many other causes. So next chart to give you some idea what's the impact of some other causes. I only show one of them. That's by increased free stream turbulence coming to this compressor from 1% to 5%, and showing that the light blue color is increased turbulence at the inlet with constant radius cut trailing edge. So you can see the pressure ratio further reduced, efficiency more in line with experiment. However, I will not say I will use 5% of turbulence for all the cases, because this number, in general, if we do it right, we will measure the turbulence level at inlet as well as the turbulence length scale. So those two numbers need to be recorded and used in our simulation. The point I'm making here is that constant radius cut have the most important impact from magenta to yellow. If a constant radius cut increase the turbulence level, the difference is much smaller than have a right geometry. Okay, now next one is I also want people to aware the CFD simulation results also depend how you average the data. So as shown in next chart. In our CFD code, we generally average the data using mass average. So when you compare the total pressure ratio, you are compare the mass average total pressure through all the K computational plane. Then all the computational plane you are doing the simulation. And this time I just simply want to show you, if I do an area average, what's the difference? With the same set of data, but two way of averaging. Okay, the magenta color is flow averaged total pressure ratio. Yellow color is the area average data. The pressure ratio reduces, efficiency reduces. I'm not promoting to area average because we believe flow average really meet flow conservation laws. However, we need to really understand how the data was acquired, how the data was reduced, and the best way of doing this is reduce our CFD data just like the people reduce their experimental data to do that comparison. So here, next chart is really to summarize what on the first examples. NASA CC3 compressor we analyzed and compare against published data. Our initial results are not encouraged at all. We have examined many causes, like what I laid out in front. Okay, 5 items: CFD, modeling, boundary condition, geometry, okay, critical feature, and look at the experiments. But we find the major issue in our simulation not matching the data is we did not capture the trailing edge shape for this design, so that we miss a lot when we compare against experimental data. Other causes such as free stream turbulence, surface roughness does not have such a strong impact on this geometry as the true trailing edge geometry. Next one, I just want to demonstrate the averaging of your data can also impact your comparison. I just want to make sure we are aware this problem and the need to work with experimentalists to understand how they reduce the data. For this root cause analysis took us about 2 months to figure out, because that's really bring us to make a new capability on our one mesh generator to make it capable of generating a mesh with a constant radius cut. So this really gives you a summary of our first examples. Second example is the conjugate heat transfer analysis of highly film-cooled turbines. I would like to have our senior CFD engineer, Will Humbert, to present this, because he went through all those causes during development of this capability. This CH simulation was supported by Air Force, and we published at the ASME conference in 2013. And without further delay, Will, would you please?
Okay, so like Bob said, this is a root cause analysis that we went through when we were developing the conjugate heat transfer capability for our solver CodeLeo. In case anybody doesn't know, conjugate heat transfer means that we run the fluid side of the simulation and then the heat conduction side of the simulation within the solid region, and we do them simultaneously in a fully coupled manner, so that all of the heat transfer information is being passed between the fluid solver and the heat conduction solver within the same code. And that really, the purpose of that really is to just give us a truly physics-based method for predicting the performance and durability of these film-cooled vanes. And so the case that you're seeing on the left, like Bob referenced, this is the Air Force Research Laboratory's high-impact technology turbine first vane. And so this vane has a total of around 650 individual film cooling holes. You can see them here on the pressure side of the vane, as well as the the ID and OD platforms. And so for the conjugate heat transfer type simulation, we're actually meshing and fully resolving each of these 650 film cooling holes. And so, to do this, we use an unstructured mesh, and in this particular case, the size of the mesh ended up being something like 20 million elements in fluid, and then 10 million elements in the solid. There we go. So here we're looking at our initial predictions compared against the data. And the data is coming from the Air Force Research Laboratory's blowdown facility. So if we look on the left-hand side of the screen, what we're seeing here are some surface contours for the heat flux and then the surface metal temperature. And so just looking at these on a high level, you can see some signatures of the film cooling holes. You have shaped hole rows back here on the pressure side. You have the stagnation line right here, and you can see there's shower head holes on either side of that stagnation line. And then on the right hand, the middle and the right, we have data, both CHD predictions and experimental data. Here we're displaying them at 5% span and 62% span. And the way to read these charts is, first the dashed blue lines in this case are the conjugate heat transfer predictions, and then the small green dots are the experimental data. Looking, from 0 to -1 on the x-axis, this is looking at the pressure side, going from the leading edge at 0, wrapping around to the trailing edge at -1. And similarly, the suction side of the airfoil is starting from the leading edge at 0 and moving back to the trailing edge at +1. So if we look at the heat flux data, you can see that the experimental data points and the heat flux predictions, they seem to somewhat line up. But there's some very high peaks that's not really captured in the data, but it's not quite clear what's going on there, because the heat flux gauges are in between the holes, and these peaks are always happening at the right near the hole. So this data can be a little bit less clear, although we felt that these peaks were maybe a little high. But now when we look at the surface metal temperatures, now this is a little more telling of what's going on. So if we look at 62% span and we just look at the suction side of the airfoil, we might think to ourselves, wow, this prediction is really good. I mean, if you look at these points, they're, for the most part, right on with the experimental data. But then, our eye is drawn over to the pressure side of the airfoil, and we see, this kind of huge under prediction going on. This is something on the order of, 20 or 25 Kelvin, which if you're familiar with turbine durability, that is a huge number in terms of the lifespan of a metal part, especially, for the hot section of the turbine. So this is something, that was kind of bizarre to us. Why is the suction side looking so good? The pressure side is looking so bad. So like Bob went through, mentioned before, there's a whole, there's a long list of things that you can look at. And we looked at a lot of things for this case. We looked at geometry difference. Are we actually simulating what's being put into the blowdown facility? Are there limitations of the analysis tools? Things like wall integration versus wall functions, turbulence modeling, different kinds of boundary condition implementations, a lot of things that can go wrong here. Also, are we just kind of fooling ourselves about what the data is telling us? Are we really understanding, what's coming out of the experiment? But looking through all of these possibilities, what we really ended up with, at the end of this analysis was, not modeling critical features, and then, are our boundary conditions correct? So I'm going to start off with, this first one, not modeling critical features. So, Bob made reference to that this one is a little more subtle because, it's not, in this case, it's, there's a difference, a feature that we didn't model, but it's not really something with the geometry. It's not as simple as a geometry difference. So if we look at the upper left-hand picture, you see, a picture of the suction side of one of these airfoils, and it's got this, shiny gold film on it. And what you're actually seeing here are the, the heat flux gauges, that are used to measure, to give those heat flux measurements that we saw earlier. And so, the gold pieces, these are the leads for the heat flux gauges. Oh. Sorry about that. And then what's really important is there's this kind of brown layer, in between. And so, how is a heat flux gauge actually, put together? And, it consists of three parts. So there's a thermocouple on the bottom. Then there's this thin layer of like an insulating material. In this case, it's called Kapton. And then on top, there's another heat flux, another thermocouple. And the idea is that you get the difference between the temperature measurements of these two thermocouples, and you're setting up the temperature difference is related to how good of an insulator that layer in the middle is. And from that temperature difference and knowing the properties of the insulator, you can get a heat flux measurement. And so, when we initially looked at this, we thought this Kapton layer, it's very, very thin, something like 50 microns. And we thought that, we don't have any way to simulate this, but really we were thinking that this is probably going to be a second or third order effect. And that wouldn't be a major player in the end results. And what we found was that was really not the case. That assumption that we had made was very wrong. And so what we ended up having to do was go back and develop some new technology that would allow us to do essentially model a thermal barrier coating, because that's effectively what this is. thermal barrier coating. And then we, once we had developed that, we came back, reran the simulations, and we wanted to see, what is the end result of this Kapton layer. And this is, so again, what we're seeing here is we have heat flux on the top, surface metal temperature on the bottom. Blue is our initial prediction that we showed earlier, and then the red curve is once we added that, that very, very tiny, thin insulating layer on the surface. So if we look at the heat flux, the first thing that we can see is, okay, we've reduced the heat flux levels, very significantly. One thing you might notice is that, these peaks that go up, these are reduced a lot, but the peaks that go down, these don't reduce much at all. And the reason for that is because just the way that this plot is generated, there's no Kapton layer inside of the actual film cooling holes. And so these peaks that go down, this is where the the numerical TechPlot probe actually goes down into the film cooling hole and pulls out the data. So that's why these are unchanged. Now looking at the surface metal temperature, again we'll focus on the 62% span. So again, our original prediction, what we saw was that we were getting it really close on the suction side of the airfoil, but on the pressure side we were under-predicting quite a bit. So now what we see when we add the Kapton layer is that, okay, the pressure side of the airfoil, it's the temperature's coming up a bit, but the it hasn't quite reached to what the experimental data is telling us is going on. On the suction side of the airfoil, however, before we were, it looked like we had great agreement with the experimental data, but now once we account for this Kapton layer, now we see, oh my goodness, now our temperature is just much higher than what the experiment is telling us. So, I mean, we've gotten one of the missing pieces, but obviously there's something else that we're missing that's very important here. So what else could be going on? So that brings us to the boundary conditions. And so what we ended up doing was we did a really detailed investigation on the boundary conditions, especially the boundary conditions as they varied around the annulus of the wheel. And so our original boundary conditions that we had applied, specifically for the coolant supply pressure and temperature ratios, they had been based on the the upstream supply pressure, what's really being fed into the annulus. Now, the way that this vane is set up, there's two supplies for the coolant. There's one that supplies this, upstream, ID cooling cavity, and that ID cavity that supplies the leading edge shower head holes, the suction side shaped holes, and some of the pressure side shaped holes. The OD, or rear cavity, supplies the remainder of the pressure side holes, as well as these trailing edge holes. So what we found was, the assumption had made was that there was, again, relatively small variation between, what was coming into the inlet of the annulus and what the vane was actually seeing. But when we looked into the data in detail, we found that, actually there was a significant amount of variation around the annulus for these coolant supply pressures and temperatures. And so here what you're seeing is the, so here what you're seeing is on the upper left-hand side, is the difference in the coolant supply ratio, pressure ratios for the initial boundary conditions and the updated boundary conditions for both that ID and OD, supply. So for the ID, which again supplies the the leading edge shower head holes, the suction side holes, in some of the pressure side holes, we're seeing, a small bump in the supply pressure ratio. Whereas for the OD cavity, we're seeing a fairly large drop in that supply pressure ratio. And correspondingly, in this lower right plot, what we see is that, we see overall a small increase in coolant flow from the ID and a moderate decrease in cooling flow from the OD. So what effect does that have on those surface metal temperatures that we saw before? So again, the blue curve here, this is the curve that we saw on the previous slide where we had added our Kapton layer. The red curve is that same, we still have the Kapton layer, but now we've added these updated boundary conditions. So looking at the pressure side, what we can see is, before we were, we had moved up the temperatures a little closer to the experimental data, but it was still a little under predicting. Now we're a little closer in the range. We're over predicting a little bit, but this is this is looking a little bit more credible on the pressure side. When we move to the suction side, now we see that large over prediction that we had been seeing once we just added on the Kapton layer. Now that's been brought down to a more reasonable level. And again, the reason for this is because we've seen an increase of coolant flow from the ID cavity, which is feeding the film cooling holes that are, driving this area over here. And we've seen a decrease of cooling flow that's driving the cooling flows that are affecting this area. So, just to summarize, what we went through here, our initial prediction, the heat flux variation seemed a little high, but more importantly, while the suction side metal temperatures seemed very nice, the pressure side was just, very significantly underpredicted. We added the Kapton layer, which, we had initially thought was like a second or third order effect, but in the end ended up being a primary driver for temperature. And we found that, that improved things on the pressure side. It didn't quite get us where we thought the experimental data was telling us. But the suction side, now this is, in need of a lot of help. And that brought us to, question our assumption about, how much do boundary conditions vary around the annulus of the wheel. And once we accounted for that, now we're seeing, very reasonable predictions, for the surface metal temperatures. And with that, I'll give it back to Bob.
Thank you. Let's go down to the next chart. Okay, so let me quickly do a summary for the example 2, the cooled turbine first vane conjugate heat transfer analysis, and compare against newly created experimental rig data. Our initial results, as usual, is not very encouraging, and most things bother us is underpredict the pressure side temperature. We really went through many causes, and some of them smaller effect, some of them larger effect. As well mentioned, we find 2 of them are critical. One is the critical feature, Kapton layer, which act as an insulator, so that results in raise in temperature on all over the place and reduce heat flux, which initial simulation was not captured or was not simulated, adding that layer. By adding that layer, it makes sense physically because insulate the surface, make the outer temperature higher, heat flux lower. It makes sense, but it's still going the wrong direction on the prediction on suction surface. So then we're working with the people who carry out experiment, look at the data, analyze the data with them together. We find out the boundary conditions should be more consistent with each experimental run and the locations. We correct that and finally make the data and allows us much closer. You may ask how long it took us. It really took us about a year to really understood to going through all this process. And a lot of people was involved. People in the Air Force, or many engineer in our end and in the Air Force end to bring this all together. This is the second example. Now I'm going to quickly go into the third examples.
All right, our third example is the analysis of a 3.5 stage axial compressor. This one is a little different than the previous two in terms of the situation. In this case, what we are doing, we are assessing CFD results when there is no experimental data to compare against. Okay, and in this case, what we had is we had a 3.5 stage compressor geometry given to us with a pre-existing mesh. Okay, this user had used Pointwise to generate was a very nice, a very dense, multi-block structured mesh for this 3.5 stage compressor. We also took the geometry for the compressor, used our code wand to generate another mesh, and we ran both of them. Okay, when we first started this, our expectation was that the results would be relatively close. But what we found was actually, it was quite surprising. First, given the same geometry, given all the same features being modeled, okay, the user's mesh, the Pointwise mesh here in blue, and the wand mesh, the speed lines for both actually were quite different. There was at least a 2% difference in efficiency and a 1.25% difference in flow rate. I also want to point out that actually the range between the two compressors was significantly different. Okay. Now the question becomes, what are the methodology? How do we debug which of these two meshes, given the fact that they are run on the same solver with the same settings? What is the difference between the two? Which one is correct? Okay. So of course, the first thing we're going to do, and I'm going to jump around between slides, is we're going to make sure that all the simulations for each of these points is converged. Okay, so we looked at that. We looked at the efficiency convergence for both the third-party mesh and our mesh. Okay, we looked at the last 2,000 iterations of the mass flow versus efficiency for every point. And the last 2,000 iterations are signified by the long black tails. Okay, these are not significantly long, so we deem that actually all the points for both simulations, for both meshes, is converged. Okay. Since we are isolated to the mesh, the next thing we wanted to look at was the number of mesh elements. Okay, the multi-block structured mesh that we were provided by the user had about 2.4 million elements, while our wand mesh that originally generated these results only had about half, or about 1.1 million elements. Okay, and I think everyone knows about grid resolution or mesh convergence studies, right? So that's what we did. We doubled the amount of elements in the flow field to match what was within the third-party mesh, and we reran the speed line. Okay, that new speed line is here in black. Okay, first thing to note is that when it comes to the efficiency, the choke, it's actually not too much different than our original mesh. Okay. Please note that efficiency, we did not run this fully to stall, so we did not really check the range for the fine mesh. But from a higher level, we can see that really increasing the amount of elements in the flow field did not really change the results significantly. So there must be something else here. And since we know that we are using our standard software, our standard CodeLeo solution, we use wall integration when we are solving these meshes. Okay, and knowing that we are doing wall integration, that means that something like y plus is an important item to check. Okay, so here is just a little bit of background information on the process. If we were to look at the flow field of the between our mesh and the third-party user mesh, they both look very similar. If we were looking at the loading on the airfoil itself, again, it looks very similar, right? But when we start looking at the Y plus of the airfoil, what we have here is in red is the Y plus of our mesh code 1. And blue is the Y plus of the mesh generated by the third-party user. Okay, so that had an average Y plus of around 5. So we know because wall integration, we're using wall integration, we know we have to have a Y plus probably less than 3 in order to have a more credible solution. Okay, so we went about redesigning or remeshing the pointwise mesh using a lower Y plus. We had access to the geometry, we had access to the topology, so we simply just reduced the near wall spacing to reduce the Y plus. And here are the results of that new mesh. So in blue again is the original pointwise mesh. In red is the wand mesh Y plus. And in green is the new pointwise mesh with the reduced Y plus. And you can see that the new pointwise mesh with a reduced Y plus is about less than or equal to 2. Okay. So we ran this new pointwise mesh, and here are the results on the effect of Y plus in terms of the solution. When we ran the simulation with the same solver and the same settings, and we compared them, we can now see that the new pointwise mesh with the reduced Y plus more closely matches our original wand calculation. Okay, because we know that we are using wall integration, we felt that this solution was much more credible than the original third-party users solution. So just to summarize what we are seeing in example 3. In this case, this is really highlighting how different users can provide you different results and what is needed to really avoid user bias when it comes to root cause analysis, when it comes to doing CFD analysis. Right. In this case, we had the same geometry meshed using 2 different mesh methodologies and by 2 different engineers. Okay, so if you were looking at this as a third party, the question is, how do you know which of the 2 users is correct, right? What we found is when we compared them, there was a big difference in choke mass flow and in efficiency. Okay, we did our root cause analysis, examining all the mesh differences, like the number of mesh elements, and looking at the appropriate mesh topology for wall treatments. But what we found is actually the Y plus value being used in the third-party engineer's mesh was too high for a credible wall integration simulation. Okay. Again, the overall effort of this was about 1 month. Okay, so that's all we have for today. I'm going to finish up with just a quick summary of the presentation. And I think that when it comes to root cause, it's really about what is needed to obtain a credible numerical result, right? And to do that, we must really understand the code's limitations and the approximations and assumptions that are being used. Okay. We have to make sure that the geometry being analyzed is consistent with the geometry being tested. And if it is not, that we know the impact of those differences. Okay. What we would recommend is that if the geometry being analyzed and what is being tested are different, it's important to list out those items. For example, whether or not something has a variable state or end wall gap, things like that. Next, we have to make sure to apply the correct boundary conditions and initial conditions. Okay, and we have to make sure that the location that we are applying them are the same between the experiment and our CFD. Next, pay attention to the critical flow features. I think this is the point where I would say you really don't know what you don't know. Okay, and we've oftentimes overlooked critical features because we just don't know what their effect is. Okay, and that is something like this was the Kapton layer for heat flux measurements. It was small, it was thin. You wouldn't expect it to have such a large impact, right? But those are the things that need to be checked and double checked. Lastly, understand the experimental setup. If you have access to the experimentalists, use them. Okay, understand how what their data acquisition techniques are, what their data reduction methods are, and what the error limits are. Okay, only through collaboration with the experimental team can you really get a true root cause analysis. Otherwise you may often find yourself unable to continue your root cause analysis process. Lastly, I would recommend this. To do proper root cause analysis really requires a lot of persistence, patience, and time. And I know that sounds like a lot to invest, but the payoff is actually quite significant. The difference between a validated software and something that is calibrated is that when you do this root cause analysis, that trust can be is built into the solver and into your methodologies. Okay, it is not something that you have to continue to go back into and check and double check every time. So with proper root cause analysis, you can build trusts by doing multiple of these root cause analyses over and over again, okay, until you are extremely confident that what you are designing is what you will get when you manufacture it. Thank you for listening today. I will now open things up for questions. If you have questions, there's a ask question button. Please feel free to click, and I'll wait a few minutes. If you don't feel comfortable asking a question, you can always email me at mlni@adscfd.com or visit us at www.adscfd.com. All right. And with that, I'll just wait a few minutes and see if there are any questions.